Alright, so this is Atoms and Bonds Part 2. In the first part of Atoms and Bonds, we just talked about atomic structure. So what makes up an atom? What parts does it have? And now we're going to review that a little bit and then get into how do atoms interact with each other and why do they interact with each other. Alright, here is the model of our carbon atom. So the first thing that we need to remember is right here in the center, that is the nucleus. That holds the protons, which are represented by the P with the plus sign next to it, and then we have 6 neutrons, which are very large particles that hang out with the protons, but they have no charge. But right outside of that, we have these rings right around here. And what they do is that's where the electrons hang out. So they are represented in the picture by these little E's with negative signs, but I'll just darken them up a little bit. So we have all these electrons. So if we counted them all up, carbon has 6 total electrons. 6. But the ones on this inner ring right here, they don't really do anything. They're not going to interact or be able to interact with other atoms. So they kind of just stay and they hang out. It's more this outer ring. This outer ring and the electrons that are furthest away from the nucleus are the ones that are going to be important when it comes to chemical reactions. Okay. So when we are talking about the electrons that are furthest away from the nucleus, we are talking about something called valence electrons. So that's the name of them. That's just another vocab term. And it just means the electrons furthest away from the nucleus, the outermost electrons. And they're important because these are the electrons that are going to be involved in bonding. So we're going to write that down real quick. You should write it down too. So these are involved in bonding, which is how atoms interact with each other. Alright, so how do we figure out how many valence electrons that a element has? Well, you're going to look right here, and I'm going to show you in just a second, but right here, there's a really easy way using the periodic table that we can figure this out. So grab out a periodic table, and we are going to give you a little hint. Alright, here we go. We have a periodic table right here. So what you want to do is start all the way to the left with hydrogen, and you're going to write sorry about that, you are going to write a 1 over hydrogen. Next one is the second column starts with beryllium. You're going to put a 2. And for our purposes, we don't care about this stuff in the middle, so we're going to skip over to boron. That's 3, carbon 4, 5, 6, 7, and then 8. So make sure your periodic table is numbered like this. And you're going to need to reference back to it when we go to figure out some examples. So what do we call these electrons that are furthest away from the nucleus, or the outermost electrons? Those are called valence. So that's our name for them. And those are the atoms that are going to be involved in bonding. So that's why they are important. Involved in bonding. So what they do is they interact with other atoms, which is really important because most of the time atoms do want to interact with each other. And what you're going to do, how you can figure out the number of valence electrons, is you're going to look at your periodic table and you're going to go from left to right. And the column that the atom exists in is the column that represents the number of valence electrons that it has. So for example, let's zoom in a little bit, carbon, if you count it over, carbon would be in the fourth column. Remember, we skipped the middle. So carbon's in the fourth column, which means it has 4 valence electrons. Hydrogen is in the first column, so it only has 1 valence electron. And I'm going to put a little star next to hydrogen, so I remember to come back to that. Chlorine is almost all the way to the right, so it has 7 valence electrons. Oxygen has 6. Remember, knowing this is important because for these guys right here, except for hydrogen, we have the magic number of 8. So what we want, sorry about that, what we want is these atoms, again, except for hydrogen, because it's so tiny, want to have 8 electrons in order to be stable. And how do they do that? How do they satisfy that? Well, they're going to bond with other atoms, and they're going to either share electrons with each other, or they're going to give up or take electrons from other atoms, depending on who is interacting with who. Alright, so now we are going to apply what we have just done, our new little trick. So for carbon, I'm going to zoom in a little bit, the number of valence electrons is 4. It's in the fourth column. Hydrogen is in column 1, so it only has 1 valence electron. Chlorine is all the way over toward the right. It's not quite at the end, but it's almost there, and it has 7. And oxygen is again more toward the right, and it's going to have 6. Now, for most elements, so in our case, in our list, everything but hydrogen, what we need to remember is that we have the octet rule. That means 8 is the magic number. So what I mean when I say that is, carbon in its outer ring has 4 electrons, but it wants to be stable. It wants 8 electrons. Chlorine has 7, but it wants 8, so it needs 1 more. Oxygen has 6, so it needs 2 more. The reason that hydrogen is not part of this is it's because it's so very small that it only has that first shell, that first ring. So I'm going to draw it for you really quick. All right, so if we're talking about hydrogen here, in its nucleus, so this is nucleus, it has 1 proton, so tiny, and doesn't have any neutrons. And then in its electron shell, it has 1 electron. And this is the first electron orbital, the one closest to the nucleus. It only has room for 1 more. It can't fit 8 in there, which is why 8 is not the magic number for hydrogen. 2 is going to be the magic number for hydrogen. So it's kind of like the exception to our rule. So that's how you figure out the number of valence electrons, and consequently, how you figure out what or how many bonds your atom needs to make. Alright, so when we talk about bonding and drawing bonds, there's a really easy way to draw our atoms so that we just really consider the valence electrons. So first, you're going to write the atomic symbol. So let's say our atomic symbol is, we're talking about oxygen. So our atomic symbol, if you look at your periodic table, the atomic symbol is, our atomic symbol is O. Alright, the next thing you want to do is you want to determine the number of valence electrons. So you got to figure out what column is oxygen in. Well, we reference a little bit back in our notes, we know it's in the 6th column, so it has 6 electrons. And we're just representing the electrons as dots right now. So we want to say 1, 2, 3, 4, 5, 6. So those are my 6 electrons. And as you can see, if I need 2 more, there's a spot for each of these. One right here and one right here, because these electrons are unpaired. So the other example down at the bottom right here is carbon. So carbon has 4 valence electrons and its symbol is C. So before they bond, atoms are neutral, which means they don't have a charge because the number of protons, or the number of positive charges, equals the number of electrons or negative charges. And we know this because if we look at our periodic table, the atomic mass represents the number of protons or the number of electrons. So everything should be equal in unbonded atoms. That's important. The atoms are not bonded at this point. They're just all by themselves. So here's our example. So oxygen, in its unbonded state, has 8 protons in the nucleus, 8 electrons, they're the greens hanging on the outside, and 8 neutrons also in the nucleus. So we have space for 2 more. We need we need 2 more electrons to make 8, or the octet rule. Alright, so when we have 2 atoms coming together, they're going to make a chemical bond. That's how they interact with each other. And sometimes we can make what's called a compound. And a compound is, so that's a vocab term. A compound, a substance is composed of 2 or more elements. So these are 2 or more different elements. So our example is, we have a couple of examples. So the first one is water, H2O. It's made up of 2 hydrogens and 1 oxygen. It's going to be right there. So 2 different elements. Then we have NaCl, which is not pictured here. You have C6H12O6, which is glucose, right down here. And we have CO2, right over here. So because they're made of 2 different elements, they are what's called a compound. And what's important to realize here is that this idea right here, the properties of the compound are different than the properties of the elements that make it up. So let's take salt, for example. By itself, Na and Cl, they are both really bad by themselves. Sodium is reactive with oxygen, it explodes. Chlorine is a gas that will do a lot of damage to you if you inhale it. But when we put them together, when they bond with each other and become NaCl, when they come together, everything is happy. And we make salt, which we can eat without harming ourselves. All right. So why do atoms do this? Why do they form bonds? Well, they form bonds because they want to become stable. So they might be unstable, like sodium in its natural state and chloride in its natural state. And what that means is we have a full valence shell, full of electrons. So row 1 elements need 2 valence electrons to be stable. So for us, that's hydrogen or helium, because they're in the first row. The rest of the atoms, the rest of the periodic table, needs 8 to be stable. And there are 2 main types of bonds that you are going to need to know, covalent and ionic. And there's a couple of rules to remember when we're talking about them. So when we talk about covalent bonds, that co in covalent, that means, and I want you to think of this, the word share. If you're on a team and they have co-captains, those co-captains are sharing the responsibility. So what's happening here is that these atoms both need electrons. So they share them to complete their valence shell. And this forms what we call a molecule. And it's formed between two nonmetals. So this idea is really important, two nonmetals. So if you look at your periodic table, you should know where the metals exist and where the nonmetals exist. So if you have two atoms that are nonmetals in the same category and they bond together, they're going to bond covalently. And think of it kind of like this. Say this is atom A and this is atom B. And the electrons that they share are kind of going to go in between them. I like to think of it like a figure 8. So this is like the electrons. They kind of go like this. And they spend time around each of them. Okay? So they're sharing. Everybody's happy because everyone has then a full valence shell. Okay. So the number of valence electrons needed to complete the shell is how many bonds it will form. So our example, or the first one, is H2. So this is hydrogen. So hydrogen, we have our two little hydrogen atoms. They each have, on their own, one electron. That's what that little black dot is. But when they come together, they're going to go like this. And this right here, that's the bond that they share. These two electrons are then shared between them. And now they are happy. And then I'm going to change this from NH4. I'm going to change that to a 3, NH3. So nitrogen has a valence number of 3, which means if I draw it, it has 1, 2, 3, 4, 5. So each of these down here needs to be paired up. Hydrogen is still 1. So what's going to happen here is it's going to look like this. We're going to put nitrogen in the middle. And we have a hydrogen over here, hydrogen over here, hydrogen over here. And they are going to share here, here, and here. Up here, these electrons were just nitrogens to begin with, so those are not shared with the hydrogens. And then the last example we have is H2O. So oxygen has a valence, it's in column 6, so it has 1, 2, 3, 4, 5, 6. So it needs 2 valence electrons. It needs 2 electrons to get to 8. And hydrogen, again, only needs 1 more. So I'm going to draw a little line there. So what's going to happen is you have oxygen, 1, 2, 3, 4. It's going to bond with hydrogen over here. And they are going to share. That is the bond. So an easier way to draw them, so you don't have to draw all the dots, is actually just represent them with lines. So what would happen is you would have H dot, H dot, and what's going to happen here is you go H, you'd make a little line. That line represents the bond. It represents the shared pair of electrons. Same thing here. So we're going to do N, 1, 2, 3. So each of these represents 2. And then H2O, oxygen with our hydrogens. And remember, oxygen has 2 more pairs of electrons that it does not share with hydrogen. All right, so there's a couple types of covalent bonds. A single bond is when they just share 2 electrons, which is exactly what you saw on the other sheet, or on the other page. And that's what's happening in water now. There's 1 line. In a double bond, they need to share more than 1 pair to be happy. And then in a triple bond, they need to share, again, more. So just know that it's not maybe not just a single bond, but multiple bonds that they are sharing. All right. So in each of the following molecules, in CO2, how many atoms are in each? So for CO2, we have 1 carbon, we have 2 oxygen. For T6H12O6, what's going to happen here is this number after it is talking about the letter in front of it. So we have 6 carbons, 12 hydrogens, and 6 oxygens. Down here, again, we're talking about the number in front, so H2O, and we should remember from our little drawing, is 1 oxygen and 2 hydrogen. Alright, so a second type of bonds are called ionic bonds. And we call them that because they form what's called ions. So atoms become ions, which means that they are no longer neutral, they become atoms with a charge. So this idea right here, people often find this confusing. So atoms become positive if they lose electrons, and they become negative if they gain electrons. And for some reason, that is hard for students to grasp. But, alright, so what happens in an ionic bond is just that, and I will show you an example, that we have these atoms that are either losing or gaining electrons, and because of that, because they become charged, they become like magnets, because positive and negative attract to each other. And that is what forms when we talk about, did not want to do that, when we talk about ionic compounds. And what's important to remember here is that this often occurs between metals and nonmetals, so between atoms of two different categories on our periodic table. Let's talk about why. So let's look at sodium on your periodic table. So sodium has an atomic number of 11. So let me just zoom in a little bit here. Here's my nucleus. I have 11 protons, and I have, if I were to do the math on this, I would also have 11 neutrons because the atomic mass is 22. And I'm going to just draw in the electron orbitals really quick. So if I know I have 11 protons, that means I'm going to have 11 electrons in an unbonded atom. So I'm going to move that over. So I can fill 2 in that first row. I can fill in the second row 1, 2, 3, 4, 5, 6, 7, 8. So then I have 10 electrons. But then I have 11 total. So I need to have 1 electron just hanging out by itself in this outer ring. And remember, my magic number is 8. I need 8 to be stable. So what happens, is it easier then to gain 7 more electrons, or perhaps to be able to give up this electron, to lose this electron? And if I did that, if I lose this electron, then look what happens. If I lose this, sorry, it's taking longer than I thought. If I lose that electron, if I give it away to another atom, which sodium really wants to do, I still have 11 positive charges. That didn't change because my number of protons doesn't change. But if I count up my electrons, take a quick count, I only have, so I have 11 protons, 11 positive charges, but then I only have 10 negative charges. So what I end up with is 1 positive charge. That's why I become positive. And the same as if I were to suddenly gain an electron. Because my number of positives don't change, so for example, if I have, and this is just a total random example, if I were to have 5 positive charges, and all of a sudden I were to gain, so it's positive, I were to gain a negative charge, then I am overall negative, because the electrons have that charge. Sorry. Okay, so let's do a couple examples. And for this, I am only going to draw the Lewis dot structures. And remember that only is considering the valence electrons, the ones that are furthest away from the nucleus, not all of the electrons that it has. So if I start, I have to draw the symbol, so Na, that's for sodium, and if I look, it's in the first column, which means it has one valence electron, which I'm going to draw right there. And remember, it has 10 other electrons. We're just not looking at them because this one is the one that's furthest away from the nucleus. And then we have Cl. And if you look, it is in the 7th column. So it's almost happy. So 1, 2, 3, 4, 5, 6, 7. So what's going to happen here, guys, is that to make sodium happy, it needs to give up its electron. And to make chlorine happy, it needs to gain an electron. It only needs one. So sodium happily gives up its electron. And what happens is we become NaCl. The Na is plus, the Cl is minus, because we added a negative charge. So the second one is MgO, so magnesium oxide. So we're going to start with magnesium. So if we start with magnesium, its symbol is Mg. It's in the second column. So it has not one, but 2 electrons in its outer shell. Again, total it has 12 electrons. So it has 10 other electrons that we're not seeing here. And that's going to bond with oxygen. So oxygen is up here. It has 1, 2, 3, 4, 5, 6. Oh, excuse me. 5, 6. So what's going to happen is magnesium has 2 electrons to give up, and oxygen will happily take those 2 electrons. And when they bond together, because they now have charges, Mg2 plus, because it lost 2 negative charges, and the oxygen is 2 minus, because it gained 2 negative charges. This attraction right here, this attraction between the positive and the negative, it's what's keeping them together, like magnets. Okay, so this is an example of sodium chloride. This is how it would associate with each other. So the big guys right up here, that's chlorine, all of these, and sodium is a lot smaller, and you should be able to tell that by the number of particles that it has. But it sticks together by these ionic bonds, so it clumps together really nicely because of that positive and negative being attracted to each other. All right, so then we have something called van der Waals forces. And we'll come back to this idea later, but they're attraction between separate molecules, so not between atoms. So this is very different, so not atoms. This is not the same thing as a chemical bond. But it's important because without it, this little guy, this gecko down here, wouldn't be able to crawl up very flat vertical surfaces. And also it's going to be important when we come to talk about water. So when we talk about atoms interacting with each other, these are chemical reactions, and we write them in the form of a chemical equation. And this vocab, reactant and product, is going to be really important in just a second. But it should be really easy to figure out what's happening here. So I'm going to rewrite this. So we have 2H2, which means I have 2 of this H2 molecule, so I have 4 total, plus O2, so I have 2 oxygen here. And then what you have is this arrow. So I like to think of that as yields. So when I add these 2 together, that's going to give me something. And it's going to give me 2H2O. Anything that comes before the arrow, right here, that is a reactant, because it goes into the reaction. Anything that comes after the arrow, think of it like an equal sign in math, that is a product. This is what we have made. This is what we have produced.